Hello, I'm Tom Hollingsworth, and welcome to Networking Field Day. We're here in sunny Santa Clara, California with NEC at Networking Field Day 13. We're also joined by a group of Networking Field Day delegates around the table who represent the best and brightest minds in the networking industry as bloggers, podcasters, writers, and speakers. They have been invited to this event to take part in discussions, to ask questions, and offer their opinions on technology. If you'd like to learn more about this event series, including how to become a presenter or a delegate yourself, please go to our website at techfieldday.com. If you'd like to see more videos about technical subjects like this, please visit our YouTube channel at youtube.com/techfieldday.
Hello, for those that joined us, my name is Liviu Pinchas. I'm the product manager for NEC SDN product line. The third use case that we will show you, will demonstrate, is for data center CrossConnect. So now we move from LAN to data center. Okay. So this picture shows exactly what we mean when we say data center CrossConnect. Now let's assume a data center with multiple tenants. Each tenant has a facility inside the data center in the yellow squares there. Each facility has a number of servers and all the networks that connect those servers and maybe even a router to access the WAN. And then common to all the tenants, there are a bunch of connections to internet. This connection can be from carriers, from cloud service providers, from business partners, from other data centers of the same service providers, and so on. And now each tenant wants to connect to one or more of the uplinks. And this is sometimes called an internet exchange. The protocols that we run to do these connections, which happen in a part of the data center that typically is called the meet-me room. So the protocols that we run, it's very simple. The model is that of a patch cable. So we would like to see practically a direct connection from a tenant, from a certain type of traffic that the tenant has to an uplink. But we don't want to use a switch or a router. We don't want to learn addresses to manage. We want some very, very simple type of connection, which is model of a patch wire. Now, CrossConnects are more complicated and bigger business than many people think. There are, first of all, critical types of CrossConnects. One example would be an equity trading firm that needs an extremely fast CrossConnect. Every milliseconds there matter. The price of the stock changes, and a lot of money is lost or won. Then video streaming companies have huge amounts of data that needs to go through these CrossConnects. So sometimes we need very large bandwidth. In many cases, enterprises want very reliable connections, so they implement redundancy and cross-connect to multiple service providers. Now, this slide wants to show the type of business that CrossConnect is. And the data below, it's from a white paper that was generated by Equinix. There are two things that we want to note in this slide. First of all, the price that tenants pay for CrossConnects, it's several $100s per month. And as an example, Equinix has more than 100,000 CrossConnects installed in their data centers across the world. So if you multiply 100+ thousands with few $100s per month, with months in a year, this is a billion-dollar business for one service provider, and for multiple service provider, a multi-billion-dollar. So pretty significant source of income for data centers. The second thing we notice here, Equinix talks about almost 6,000 CrossConnects that they edit in a quarter. So there is a very dynamic nature of this business. They need to add CrossConnects on a daily basis. And of course, adding patching cables, it's impossible. So there needs to be a solution that it's fully automated and very easy to manage. And this is what we are trying to offer. So first of all, let's take a look at the protocols that it's run in the meet-me room. There are several ways to implement this. Many companies today implement this using MPLS routers. So they take all the traffic, put MPLS labels, and then they have a bunch of routers in the meet-me room that forward the data. Of course, MPLS routers are expensive pieces of hardware. They can be like 3 to 10 times more expensive than Ethernet switches. It would be very nice if we can offer a solution based on Ethernet switches instead of MPLS routers. So this is where our solution comes. Using our SDN technology, we offer a bunch of circuit-oriented Ethernet connections in which we forward the frames based on an added VLAN. So instead of adding an MPLS label, which forces us to use an MPLS router, we use added VLAN that can be handled by regular switches. And the protocols that we run, it's forwarding based on port number VLAN ID. So on the left side of the image, you see different tenants, Enterprise A, streaming service, and on the right, different uplinks, different service providers, cloud service provider, video content provider. And we will take the traffic that comes from the tenants, look at the port number and VLAN, and forward it to the appropriate uplink, the appropriate service provider. This, of course, is not switching, it's not routing, it's just a different way of forwarding data. So our solution is based on the SDN controller and a bunch of switches. It has big advantages, mainly in the way it's managed, because the SDN controller can manage the network globally. So we don't have to go and change the ACL list of each and every switch in order to forward based on VLAN and port ID. And then when we add switches, we don't need to redo all the switch configuration. So we can do this from a central console for the whole network. And the network is discovered automatically by the SDN controller. So if we need to grow and we add some switches, we don't need to change our script. The SDN controller will recognize the new switches, will take advantage of their presence, and the same setup at the network level will be reused. We of course support VLAN duplication, so we forward based on port and VLAN. There is a low latency. We can define our routes as we want. And of course, we can have also multipass. We have multiple paths through the network, and manage them for redundancy. Okay, so this is the physical view of the solution. It's a stack of hardware. At the top, there are 1 or 2 servers. that can be NEC servers. We can provide the SDN controller preloaded on one of our servers, so it can be installed immediately, or we can provide it as software that is installed on one of the customers' servers. And a bunch of switches depends on the capacities that is needed. These switches can be, any type, 1, 10, 100 gig, and so on. And this is a block diagram of how everything works. In the servers, we run a programmable flow controller, which is the SDN controller that communicates through each and every switch through open flow. And then this is a physical view of the network. A completely different view is a virtual view, where all the switches appear like one big packet forwarding mechanism. The user doesn't care how many switches he has and how they are placed. He will just introduce commands. I want to connect these ports here on switch 5 with that port there on switch 10, and send from here to there traffic with a certain VLAN. So we have CLI commands that we'll see in a moment that specified switch number, port number, VLAN ID, and where to send it. That's all that needs to be programmed. And again, if we add more switches, the network discovery is automatic, and we don't need to change the script. This makes it very easy to add many connections per day, like we saw it's needed in the use case.
So are you targeting this platform, for like carrying through hotels, is just the interconnect between, the meet me rooms and the top of rack for the client extensions, which today would typically be just a passive set of patch panels? Right.
It is a replacement of the patch cables in many applications, including data centers. Yeah.
Okay.
Yeah, so what we are going to see, it's a small network of several switches, and we'll have traffic generators all around the switches, and we'll send traffic, and we'll route it. We'll forward it based on VLAN, switch number, port number. So that's a different protocol. It's not switching, it's not routing. It's a specific protocol that emulates a patch panel.
So maybe I'm just not following this. So today, typically these patch panels, it's just a physical CrossConnect, physical transport of it could be Ethernet, it could be some type of optical service, or a copper service.
Yes.
So in your solution, because you were talking about VLAN ID, so is this really just targeted at Ethernet extensions for Ethernet CrossConnects, or are you trying to replace the entire support for the entire physical CrossConnect plant?
Yeah, so currently CrossConnects are done with physical cables, with physical patch panels, are done with MPLS routers, in which the packets are marked with MPLS labels and forwarded based on the MPLS labels. Or there are special types with optical CrossConnects and so on. So what we try to do is to replace all this with basic Ethernet switches and label the data with additional VLAN that can be generated in the top of rack switch or router, and can be removed when the packet gets out of the network. And everything to be easy to maintain, easy to manage. Of course, it works for Ethernet traffic, not for T1E1 or optical or something.
Right.
So, please.
Hello. All right. So, my name is Mohammad Arif. I'm a system architect at NEC Corporation of America. And I'll take you through to the last and a brief demonstration of port connect function of programmable flow controller. This function is responsible for, it allows the traffic to transparently go through the input port and directly to the output port in an open flow network. That's a transparent bridging. And this particular function can be utilized to realize the data center cross-connect use case. So we have a simple topology here. There are 3 open flow switches. There are 3 VMs or machines connected across these 3 switches. What we're going to do is we will just create policies on the programmable flow controller that this kind of a traffic we want to transparently transfer from input switch, input port to this output switch, output port. So a very short demo. As you can see in the topology, there will be a tagged traffic which will go from VM1 to VM2. And if it is an untagged traffic, then from VM1, it will go to the VM3. So in the similar case, we can define multiple policies, creating the combinations of ports and VLANs, and we can transfer the traffic to multiple machines, to multiple switches. So let me try to demonstrate a simple all right. So this is the PFC which we have opened, wherein we are going to set the policies or the port cross-connect tunnels we're going to configure. And these are the 2 machines, VM1, VM2, wherein we'll try to create a connection between them. So since we have not created any tunnel, so you can see right now there is no communication going on between the machines. And now what we're going to do is we'll configure tunnels and see how this communication goes through. All right. So as you can see, currently in the controller, we have not created anything. So instead of writing, I'm just copying paste. I'll show you. All right. So as you can see, this port XC is the command which is going to create a tunnel for the transfer. Then we have mentioned the data path ID of the input switch, and then the input port, then the type of traffic which we want to send. That is an untagged traffic. And if I scroll it, it shows the output switch and the output port. This is it. So this tunnel is a unidirectional tunnel. So if we want a 2-way communication, then we have to create 2 tunnels. That is why I have created the port XC2, which will ensure the communication. As soon as I commit, these tunnels will be created, and the communication between the machines will start. So this is an untagged traffic which is going on from this machine to this machine. In the same way, if we want to ensure the tagged traffic to be going from between these 2 machines, we can create subsequently 2 more tunnels. In addition to these tunnels, it also has the recovery. So if there is a path failure, it will change the path accordingly. The controller will make it sure. If we want to look at the information of these tunnels, then we can go to, and there are various ways we can look at the switch and look at the information. we can go through the summary or the information. Sequence number is the unique ID of this tunnel, that is 1 or 2. If we go through the sequence number, let's see the first one. Let's look at the summary right now. So what it's going to show is whether this tunnel is active or it is inactive, or if there is any fault, then it will try to give you a reason behind it. Maybe the link is down or something like that. Then it will show you the path, like how the tunnel is configured, what is the input of this tunnel, what is the output of this tunnel. If we dig it further, we can look at more details like the statistics of this tunnel, how many packets, octets are going through, and also the path information. So if you look at the path information, so port 3 is connected to this switch and the output port is port 47. And then it's going to the port 47 of switch number 2, and the output port further is 3. So this is the information which we can get. So this is it from my side for the demonstration of tunnels. So it's a simple topology, nothing more. It's like you just have to mention the input, the output, that's it. And the controller will make sure how to create the entries in the switches to enable this communication.
Does this technology here handle some of the typical data center connect kinds of issues like dealing with layer 2 flooding, containment, and things of that nature?
Layer 2 flooding is not addressed here, so we are creating a channel. So the layer 2 flooding is not addressed in this case. We are creating a channel. So the typical model is, instead of using the patch panels, so we are using the switches which are going to do intelligent patching. So that is how this can be, this can be told.
So I guess, the value for, colo spaces and data centers is that, once they've patched to the top of rack, if they need to do reconfiguration of patching them between racks, it's just simply going into the command line and patching two ports together now, right? They no longer have to go out and physically, move cables around to go between one rack to another. Or to the meeting room.
For example, let's say a new service provider is added to the meet me room, and there are 50 tenants that say, "Oh, I would like to be connected to that particular service provider." So this would mean like 50 cables to add. With this technology, it's like 50 command line inputs, and this is done immediately.
Okay, so that's maybe I'm not quite following, but that seems less like just a patch system, but more kind of like a Ethernet aggregation service. A lot of carrier hotels kind of have an exchange type of service where, is that kind of what you're looking more, is more the exchange?
That's exactly the exchange,
okay,
yes.
Got it.